Hi, I'm Barbara Fox, and I had to figure out how all the different components in our broadband solution work together. And so I thought I'd make a YouTube video just to share. I had the same cable provider for about 20 years. And so after 20 years, my connection was pretty slow. So I looked at a ISP that did fiber to the home, looked at their different packages, picked one and ordered it. They sent a truck to the house. A tech jumped out of the truck, worked in my house for a few hours, and then I had a gig to my house. I was very happy. So how did it look to the tech? So the ISP sent a work order and a customer record to the tech. She pulled an ONT or ONU off her truck as well as a residential gateway. She sent the MAC addresses of both to the ISP. And then the ISP sent the MAC address of the ONU and the SLA to the PON controller, and the MAC address of my residential gateway and my SLA to the Radius server. The tech installed everything in the house. She tested the Ethernet to make sure that it worked, and then she tested the internet to make sure it worked, gave it a thumbs up, told the ISP, you can start charging her now. So how did it look to the ISP? So my house was already wired because I had cable already. And the ISP already had OLTs in my neighborhood and ONUs at other people's homes in my neighborhood. So after the tech installed the ONT and the residential gateway, sent the MAC information back, the service provider sent the ONU MAC and my SLA to the PON controller database. Then the PON controller pulled the information and configured my OLT, and then configured the ONT at my house. So if it needed new firmware, it downloaded the new firmware to the ONT, and then it configured the services that I had bought, which was voice, video, and data. Next, the service provider sent my residential gateway MAC address and my SLA to the Radius server. And then when my residential gateway came online, I sent a DHCP request to the BNG. The BNG sent a request to the Radius server and said, I just got a request for authorization from this MAC address. Is that okay? And the Radius server says, yep. And this is the SLA that you should assign to that user. So the BNG sent a DHCP address back to my residential gateway and an XTOP that'll be used for forwarding traffic to the internet. So at that point, the residential gateway is ready to send data. So it sends data through the Metro network, up the access link to the BNG, and then the BNG sends it out the network link to the internet. And so I'm online. Now, if I wanted to, I could say, oh, I didn't buy enough bandwidth right up front. I need to change the amount of bandwidth that I want to buy. And so at that point, the service provider just sends another message to the Radius server saying, oh, she's upped her bandwidth, change your bandwidth. And the BNG just changed the amount of bandwidth that I can get for throughput to the network. Now, the other thing is that the government might think I'm up to no good and they want to tap my line. They want to see all the data that I'm sending to the internet. And in order to do that, the service provider will tell the BNG, send all of her traffic to a lawful intercept server. So the BNG will take any data that I send, encrypt it, and send it to the lawful intercept server. Now, there's a mandate that any service provider has to be able to provide a subscriber's data stream, whether the subscriber is a home or a business. If the government provides a warrant, then the service provider has to be able to send the data encrypted to a lawful intercept server. So the first thing we're going to talk about is the PON controller. Now, the OLTs are actually plugs that are plugged into these routers. So the PON controller can be on the router that contains the plugs, the OLT plugs, or it can be in the cloud, or it can be in both places. And so what happens is when the OLT comes online, the PON controller configures it. And this is all done at layer 2 because we don't have internet connectivity yet, right? OLT is bringing up Ethernet. So the OLT can be managed by either the PON controller on the router or in the cloud. And then the PON controller will also manage the ONUs in the network, and it will do that using OMCI. Now, OMCI is a standard protocol now. Previous broadband solutions were really closed solutions where the OLT and the ONU had to be from the same vendor. Now with OMCI, you can use different vendors' ONUs than their OLTs. So it's an open solution as the next generation of these broadband solutions. Now the ONTs or ONUs have to be within 60 kilometers of the OLT. The OLT is connected to the ONUs through a splitter. So the further away the ONUs are, the fewer ONUs can go through the splitter. So if you're about 60 kilometers away, then really you can only support 2 nodes through a splitter. If you're within like 10 kilometers, you can support 128 ONUs through the splitter. So that's just something to keep in mind. Okay, so now we're going to move to the next part of the solution, which is the BNG. So why would you want a BNG? So a BNG authenticates a customer as a paying customer. If the service provider is doing usage-based billing or has any sort of usage-based services, the BNG can count usage using radius accounting. There's enforcement of the QoS, right? What package you bought, you get that much bandwidth. If the service provider wants to sell ACL subscriptions or be able to black hole URLs, you can do that through the BNG. Again, a service provider has to support lawful intercept. Doesn't have to do it at the BNG. You could have a lawful intercept server somewhere else in the network. It's just much easier to do it at the BNG. And then the BNG supports address pools. So the BNG can distribute different kinds of addresses, IPv4 addresses, IPv6 addresses, public addresses, or CGNAT pools. So the BNG is implemented with control and user plane separation. The CP has a view of the entire network. It has address pools. It has QoS policies for the bandwidth and reachability that they're selling. If you want to black hole some traffic, you can do it with these ACL policies. And then it creates subscriber groups. And what you do with subscriber groups is you assign users to a subscriber group, and that assigns the subscriber to a particular address pool. And in that way, the CP can control the routes in the network. And then the user plane takes in layer 2 traffic and sends it out to the internet as IP traffic. So what it does is it looks at the SVLAN on which the subscriber entered the access link of the UP. It uses that SVLAN to determine what subscriber group the user is in. And then it assigns it a particular IP address based on that subscriber group. Then it maintains a mapping of the SVLAN, CVLAN MAC address to the IP address that was assigned to that subscriber. And the IP address can be a public IP address or a private IP address. You could do CGNAT here, or you could do CGNAT deeper into the network. So all the traffic comes in as layer 2 traffic. The UP looks in its table, it translates it to IP traffic, sends it out into the network. When it comes in as IP traffic, looks it up in its table and sends it back to the subscriber as Q and Q traffic. So the CP also manages the balance of subscribers in the network. So in this example, UP1 is supporting subscriber group 4 and 6. And subscriber group 4 is any traffic that comes in on an SVLAN of 1404 is assigned an address from the 10.4.0016 address pool. Any subscriber that comes in on 1405 or 1406 is assigned an address from the 10.6.0016 pool. This is the active UP for these subscriber groups. Now on UP2, we support subscriber group 2 and subscriber group 3. Now for us, this 10.2.159.0 is a public address. The way our corporate network is, this is a public address for us. So anything that comes in with a 1202 SVLAN and a CVLAN of 2000 gets an address from this public pool. And anything that comes in with an SVLAN of 1203 gets an IPv6 address. UP2 is active for subscriber groups 2 and 3, and it's the backup for subscriber groups 4 and 6. And UP1 is the backup for subscriber groups 2 and 3. Now, the other thing that happens is UP1 advertises this 10.4/16 and 10.6/16 routes into the network. So any traffic that comes into the network in one of these pools is routed to UP1, the same for UP2. They advertise the address pools into the network so that traffic is routed to them. Okay, so this is an example of having two UPs in the network. So I have a residential gateway A, and it sends its DHCP request to the two UPs over pseudo wires. And it sends it with a SVLAN of 1400 and a CVLAN of 2000 and its own MAC address. And UP1 says, oh, UP1 supports subgroup 1400, UP2 supports subgroup 1201. So UP1 says, oh, 1400, that's me. And so it says, okay, I'm going to put into my table 1400, 2000, the MAC address of RGA, and I'm going to assign you an IP address of 10.12.158.6. And your next hop is going to be 10.12.158.1. And it sends that back to the RGA. Now, RGA says, okay, where is 10.12.158.1? UP1 says, oh, that's me, sends back the MAC address. And then from then on, RGA only forwards traffic over that pseudo wire so that all of its traffic goes into UP1 and out to the internet. It doesn't send any data on UP2. Now, RGB comes online and it says, oh, I need a DHCP address, and it sends it with the request with a SVLAN of 1201 and a CVLAN of 2000. UP1 says 1201, not me. UP2 says, oh, 1201, that's me. And so it assigns RGB an address of 10.12.159.8, and it puts the SVLAN, CVLAN, and MAC address into its table. And then RGB ARPs for the 10.12.159.1 gets back an address and only forwards the traffic through UP2. Now, the MAC address that it gets when it ARPs for the 10.12.159.1 is actually a VRRP MAC address. And so it receives that, it sends it forward. Now, UP1 and UP2 are running VRRP between them. And so UP2 says for 10.12.159.1, I'm using this VRRP MAC address. So if UP2 goes down, UP1 notices, and it sends to any subscriber with a SVLAN of 1201 a gratuitous ARP that says, to get to the MAC address associated with 10.12.159.1, come to me. And so instantly, RGB will stop sending its traffic to UP2 and start sending its traffic to UP1. And that's how redundancy works. And this is just showing you the offer of MAC address. It gives you the next hop router ID. So when you're going to configure the different components of the BNG, the CP manages the QoS policies, the address pools, the subscriber groups, and the ACL policies. The UP configures the network connectivity, IP, BGP, BFD, and subscriber group redundancy, VRRP. Subscribers are managed by configuring and sending commands to the radius server. So authentication, authorization, initial policies, changes in authorization, and lawful intercept requirements. That's how you can think about how to manage the different components of the BNG. So the third part of this solution is really the metro network itself. And so what are the requirements for architecting your metro network? It has to be scalable. You have to be able to support the PON controllers and the BNG subscribers. And you can use zones to increase the numbers. So say your BNG supported 1 million subscribers, you might have 2 different zones to support, 2 million subscribers if that was necessary. It needs to be resilient, obviously. You need to support layer 2 connectivity, and you need to support layer 3 connectivity. So layer 2 is for the PON OLT connectivity, for subscriber connectivity to the UP, and for resiliency between the UPs. And then you need layer 3 connectivity for the network connectivity for peering and forwarding traffic. So you can actually choose any underlay technology that meets these requirements. We chose to use segment routing as our underlay. And we used ISIS with segment routing and BFD because it's easy to set up, it's very resilient, and it supports layer 2 and layer 3 connectivity over top. And so we can run unprotected pseudo wires over the ISIS segment routing TILFA tunnels, and they'll be protected by segment routing TILFA. And the same with the IP routes, right? Everything is protected in the same way by segment routing with TILFA. So the way we configure it is we configured loopbacks on each of the nodes in the network, and we use that same loopback address for both ISIS and BGP. So we have segment routing with TILFA running through the network. Our PON controller and our UPs are clients to the network. They're not participating in ISIS. They're not part of the segment routing domain. They're just CPEs to their peers. And then we have an internet connectivity, and we have both a switched and a routed connection to the internet here. And we'll talk a little bit more about why we did that in the upcoming slides. So for layer 2 connectivity, we're using pseudo wires. The pseudo wires are set up with targeted LDP. We're running VPLS L2 VPNs on the different devices. And so we're doing MAC learning on each of the devices. We have to do MAC learning because we need to know at which port a particular subscriber should be forwarded. And then the AGs are learning all of the MAC addresses for the subscribers in their PEs. So we have pseudo wires to the UP hosts. That connectivity could be per OLT or it could be per PE. We do it per PE. It really depends on the scale of your network. You can, decide based on the number of your subscribers. And then we're running lag between our BNGs and their next hop. And the reason that we're doing that is because, say these were two 10 gig links, we have a lot less upstream traffic than downstream traffic. So say we had 2 gig of traffic upstream, our downstream traffic would be limited by the 10 gigs on this network link. So what we do is lag them together so that we can use more for the downstream traffic. Now, the nice thing about scaling with pseudo wires is that you can break your network into different parts. So this aggregation device is learning all of the MAC addresses of all these devices. Depending on the device that you have here, your MAC learning tables may be limited. And so if you're starting to reach the limits of your MAC learning table, what you can do is deploy another set of UPs and another set of aggregation devices. And so these guys don't have to talk at all. This is completely separate, but the CP knows where every device is in the network. So you can limit the amount of learning that has to be done by the routers, but the CPs know where everything is. So it's a nice way to scale your network. Now, for layer 3 connectivity, you could have an IP interface that originates on the UP and terminates on the internet gateway. And we did do that at one point. But we think that the better solution really is to implement BGP. And so what we did is we have iBGP running between the nodes that have internet connectivity. So these have connectivity to the routes on UP 1 or 2, and these have internet connectivity to the routes on UP 2. Here we have internet connectivity to a BNG blaster. It's a test set that we're using to generate lots of IPOE and PPPoE subscribers. And this is the network interface for that. Because PE1 doesn't have any internet connectivity, it's not participating in the iBGP connections. Now we have eBGP between the UPs and their peer, and we have it to the internet. And these are eBGP connections, and they're running BFD. So we advertise the eBGP connections into the layer 3 VPN. We're redistributing a connected route for our BNG blaster. we're running BFD on the BGP connections because we need to know if the interface goes down. We're running lag, so the physical interfaces might stay up, but the network link might go down. The same would be true if we were originating our interface on BNG and had a layer 2 underlay to our internet gateway, and this was just one IP interface. Anytime that there's a layer 2 underlay for your network connection, even if it's just one hop, you better run BFD. Now, say you didn't want to implement a BNG in your network. Say you're a small service provider, and they're really just doing last mile backhaul for an upstream service provider. In that case, everything's going to be running layer 2. You're going to have pseudo wires for subscriber backhaul. You're going to backhaul the traffic to routers in the upstream provider's network. And the upstream provider is going to run VRRP to be able to advertise routes for scale. So it really works in a similar fashion to mobile backhaul, right? This is how mobile backhaul works. Now, say you didn't have an upstream provider and you just wanted to run the VPN with no BNG. Now this whole network is Ethernet only, and we have VPLS MAC learning on each of the nodes. So all of this is learning VPLS, and then you're going to have a connection to the internet. In our case, we only have one way out of the lab. All of the traffic is switched out of the lab. So it's switched to a router in our corporate network. Basically, they've assigned us 2 subnets. So we have static routes for 2 subnets that brings all the traffic back into our lab. So we're switching the traffic out. We're going to what we consider the internet, which is our corporate backbone. And we have 2 static routes that switch the traffic back into the network. All of the traffic is reachable using Ethernet connectivity and MAC learning. Now, a better way to do this might be with layer 3 VPNs. And so we have Ethernet for PON, and we have to get to the DHCP servers. And the DHCP servers are going to assign an IP address. Now, if you have a lot of subscribers, you really don't want to do this, right? Because you have to be strategic about how the DHCP server is allocating IP addresses to the different users in the network. You don't want 1111 to be on PE1 and 1112 to be on PE2 because you don't want all of the routers in your network to have a whole bunch of /32s for all of your subscribers, right? So you want to strategically allocate your IP addresses so that you can aggregate routes. So that's something to keep in mind. We create IBGP in the network between everything, basically anything that has access to an egress to the network and any of the PEs that have OLTs in them. The aggregation routers act as route reflectors. They're at the head end. So they're acting as route reflectors. And in the L3 VPN, they are the hubs and all the PEs are the spokes. So all the traffic is being learned this way. So all traffic is going to go through the aggregation routers. Now, static routes will be used to advertise the upstream routers. So say this was your 000, your default route was to one network, and say this was a GCN, say it was like Microsoft, and they were only going to advertise the specific routes for their network. Those would be added in this way. Or say that these were 2 upstream providers that both provided default routes. Maybe you want to prefer one, say this was Lumen and they gave you a better deal than this, then you want to prefer this route using BGP so that you send all your traffic out this interface until you have too much traffic, and then you start using the second interface, and it's there for redundancy. So now to talk a little bit about QoS. So the way that communication between the OLT and the ONU works is that when the ONU has traffic to send, it tells the OLT, I have traffic to send. And the OLT knows what its SLA is. And so it says, okay, you can send me this much bandwidth. And then another OLT says, oh, I want to send you some bandwidth. And they say, okay, you can send me this much bandwidth. So what happens is basically it grants bandwidth slots to all the ONUs. So it says, you go, you go, you go, you go. But because it's told it how much bandwidth it can send, it doesn't have to do any policing or anything. It can just forward the traffic out the interface upstream. So this is all the upstream traffic. On the downstream, the OLT does not do shaping. So it relies on the router to do shaping. Now, the router could do shaping, or we could do it at the BNG. So the BNG also has all of the subscriber information for all of the subscribers in the network. And so it can do shaping at the BNG. So when traffic comes in from the internet, the BNG can say, that's too much traffic. That's more than we're going to give you. And it can just throw it away here. And then you don't send traffic that's going to be thrown away later through your metro network. The BNG will shape the traffic towards the subscribers, and it will also shape the traffic towards the network. Now, the PEs can also shape towards the subscribers. You might want to do that. They're also going to shape upstream, right? So if you have a bunch of OLTs in this PE, they'll just run through them in a round robin and shape the traffic out to the network. And also, you're going to have prioritization for your queuing so that your voice traffic goes out before your data traffic, and that is going to have to be configured on your nodes. I'd like to talk about how the technical solution fits into the business processes. So at the front end, you need to be able to order services. You need to be able to generate a work order for the tech. Then you have to figure out how are you going to associate the ONU and residential gateway with a particular subscriber. Now, either the tech sends the information back to the ISP or it's pulled from the network in some other way. The PON controller can't determine the customer ONU RG mapping because traffic is going through that splitter. So it's passive and it can't figure it out. The service provider needs to be able to push subscriber policy to the PON controller. And so you need a northbound interface on the PON controller. And you need to be able to push subscriber policy to radius for the BNG. And so you're going to load a dictionary that's particular to that BNG, that vendor BNG, to the radius server so that they can communicate back and forth. On the back end, the government's spending a lot of money to bring broadband to rural areas. And so they're requiring that any service provider that takes their money run tests and send them the results. And so what you have to do is you have to generate tests from residential gateways, throughput and latency testing, and send the results to the government. So that's it. There's a lot to it, but it's pretty interesting. There are a lot of pieces, but they work together really well. So hope this was helpful, and good luck with all you're doing. Take care. Bye.